Nice to meet you. I'm Prof.Joun, working for GNU in the Republic of Korea. The subject of this lecture is the equation of motion or equilibrium, especially for large deformation case. You'd better refer to these references for some more detailed knowledge on this topic. First, we are going to review the material derivative with respect to time parameter. We already studied on deformation of balloon element. The balloons of a tetrahedral in spatial and material coordinate systems are defined by this and this relations, respectively. Since a line element denoted by lowercase dx in spatial coordinate system can be expressed by the uppercase dx pre-multiplied by deformation coordinate tensor f. The balloon of a tetrahedral can be described by this equation. Employing these two relationships, we can derive this equation. That is, lowercase dv equals the determinant of deformation coordinate tensor multiplied by uppercase dv. After all, we can express d small v, d large v equals the determinant of f, which is defined by Jacobian, denoted by J. Now, let's study material derivative of Jacobian with respect to time. Without loss of generality, we can express the Jacobian as this relationship. Differentiating both sides of this equation with the chain rule applied, we can express the material derivative of Jacobian as a trace of velocity gradient multiplied by Jacobian itself. It can be seen from this equation that Vi, the trace of velocity gradient, should be zero if the density does not change in case of incompressible materials. From now on, we'll better use uppercase V0 for uppercase V and uppercase V for lowercase v to avoid confusion between volume and velocity, which all used the small character v previously. That is, small character v here and small character v here stand for volume and velocity respectively up to now. Applying material derivative with respect to time on both sides of this equation, we can obtain the material derivative of balloon element with respect to time parameter like this, because dv0 is fixed. The areas of an area element in material and spatial coordinate systems are defined by this and these relations respectively. Now, let's transform the area for the area element in spatial coordinate system into that in material coordinate system in the same way with the balloon element we did previously. Up to this point, the procedure is straightforward. We assume an identity matrix between FIL and the X1K in order to develop it furthermore. Employing these relations and initial notation of cross product of two vectors, we can derive this relation between two areas in the spatial and material coordinate systems, which is of great importance to explain the stresses for large deformation problems. In the spatial coordinate system, a stress vector, which means force per unit area at a point, is defined by this relation. The stress vector is defined at a point, and its value is dependent on the direction specified by unit vector n. Coded stress is defined by this equation. That is, sigma ij equals j component of force per unit area exerting on the plane normal to unit vector EI or XI axis. In the spatial coordinate system, the actually deformed material is denoted by balloon V and its boundary S. The equation of motion is thus able to be expressed by this equation, which means that summation of force exerting on the surface S and in the balloon V should equal the change of its momentum. The surface force is owing to traction, while the balloon force is caused from body force. Applying the relation between dV and dV0 to transform the integral in the spatial coordinate system to that in the material coordinate system like this, and some simple arithmetic operations, we arrive at a conclusion that this equals this. Therefore, we can obtain this integral equation. Applying this Cauchy's formula and divergence theorem, we can obtain this integral equation. This equation should be satisfied for any volume element, and thus the integrand of this equation should be 0. This is called equation of motion for dynamically driven system and fluid mechanics, while this is called equation of equilibrium for solid mechanics, in which acceleration terms can be neglected. Now, let's define the stress in the material coordinate system corresponding to Cauchy stress in the spatial coordinate system. We define the normal vector denoted by uppercase N, stress vector by T0N, and the area of the surface element by ds0 in the material coordinate system, corresponding to lowercase n, Tn, and ds in the spatial coordinate system, respectively. Now define the first pure Kirchhoff stress denoted by sigma cap, which meets this condition, that is, the force does not change between two coordinate systems. Applying this relation, we can express the first pure Kirchhoff stress as this relationship with Cauchy stress. Because the surface force exerting on the surface element ds and ds0 owing to Cauchy stress and the first pure Kirchhoff stress in the two coordinate systems, respectively, should be the same. We can transform the surface force from the spatial coordinate system to the material coordinate system, as described in this relation. Likewise, we can express the body force in the material coordinate system like this equation. As a consequence, we can derive this equation of motion based on the first pure Kirchhoff stress, especially for large deformation problems. Unfortunately, the first pure Kirchhoff stress is unsymmetric. Pre-multiplying the first pure Kirchhoff stress by the inverse of matrix F, which is the deformation gradient tensor, we define the second pure Kirchhoff stress like this, which became symmetric, of course. The first pure Kirchhoff stress can be thus expressed simply by the second pure Kirchhoff stress like this. Substituting this relation into the equation of motion in terms of the first pure Kirchhoff stress, we can obtain this equation of motion in terms of the second pure Kirchhoff stress. This slide summarizes the definition of three stresses, including Cauchy stress, first pure Kirchhoff stress, and the second pure Kirchhoff stress, their relationship and their corresponding equations of motion.